Hello audience. Today we will discuss about the how noises will be impact on signal integrity of the systems. First, we talk on what is a signal integrity, SI? Signal integrity, SI, signifies the signal's ability to propagate without distortion. Signal integrity is nothing but the quality of the signal passing through a transmission line. Fundamentally, signal integrity issues must be taken care of during the PCB design phase. Once the PCB has been designed, there is little one can do to improve signal integrity. When we have signal integrity issues in a PCB, it may not work as desired. It may work in an unreliable manner, works sometimes and sometimes not. It may work in the prototype stage, but often fail in volume production. It may work in the lab, but no reliably in the field. It worked in older production lots, but fails in new production lots, etc. A signal is said to have lost its integrity when it gets distorted, that is, its shape changes from the desired shape. Unwanted electrical noise gets superimposed on the signal, degrading its signal-to-noise ratio. It creates unwanted noise for other signals and circuits on the board. Factors that can contribute to signal integrity issues in a PCB. The most important cause of signal integrity issues in a PCB is faster signal rise times. When circuits and devices are operating at low to moderate frequencies with moderate rise and fall times, signal integrity problems due to PCB design are rarely an issue. However, when we are operating at high, RF and higher, frequencies, with much shorter signal rise times, signal integrity due to PCB design becomes a very big issue. Fast signal rise times and high signal frequencies increase signal integrity issues. Signal degradation due to uncontrolled line impedance discipline. Signal degradation due to line impedance discontinuities. Signal degradation due to propagation delay. Signal degradation due to signal attenuation. Crosstalk on one conductor due to other conductors. Issues caused by power and ground distribution network. EMI and radiation from the system. During travel on the line, if the signal encounters changes or non-uniformity in the impedance of the line, it will suffer reflections which cause ringing and signal distortion. Moreover, faster the signal rise time, greater will be the signal distortion caused by changes in uncontrolled line impedances. As we mentioned earlier, if the signal encounters a discontinuity in impedance during its travel, it will suffer reflections which cause ringing and signal distortion. Signals take finite times as they travel on a PCB from source to receiver. If data signals and clock signals do not match in overall delays, they would arrive at different times for detection at the receiver, and this would cause signal skews, and excessive skew would cause signal sampling errors. As signal speeds become higher, the sampling rates are also higher, and allowable skew gets smaller, causing greater propensity for errors due to skew. Higher frequency components of signals will suffer greater attenuation than do the lower frequency components. This causes reduction in signal band fault width, which then leads to signal distortion by increase in signal rise time, and excessive signal rise time increase results in errors in data detection. A fast voltage or current transition on a signal line or return path plane may couple onto adjacent signal lines, causing unwanted signals called crosstalk and switching noise on the adjacent signal lines. The coupling occurs due to mutual capacitance and mutual inductance. If there are discontinuities in transmission lines, usually inductive coupling dominates, and switching noise results. And as always, faster rise time signals create more crosstalk and switching noise. Power and ground paths have very low, but finite non-zero impedances. Ground loops need to be kept low. Signal degradation due to EMI. EMI increases with frequency and faster signal rise times. Radiation far field strength increases with frequency linearly for single-ended signal currents, and squarely for differential signal currents. Differential signaling. The benefits of differential signaling are mainly seen in high-band fault width, high-density systems where much low error rate data links are needed. Differential signaling gives protection to common mode electrical noise that is present at significant levels in many applications. Common mode noise tolerance. It is essential to maintain the symmetry of the differential pair to prevent the conversion of common mode noise to differential mode noise. The reflections and impedance mismatch in the common mode will not affect the differential mode performance as long as the two modes are placed perpendicular to each other. Controlled impedance is the characteristic impedance of a transmission line constituted by PCB conductors. It is relevant when high-frequency signals propagate through PCB transmission lines. Controlling impedance of a PCB trace is required to propagate signals without distortion. The factors that influence impedance are the PCB material's dielectric, the trace thickness, width and height from ground plane. We Croydon Services Private Limited will help you to design solutions with signal integrity and power integrity compliance as per EMC standards. You can reach us with your requirement on info@croydonservice.com or visit us on www.croydonservice.com. Thanking you.